titanium white? Oh,
I don't know what titanium white looks like.
Probably
Metallic white.
maybe.
Dude! It actually solidified into acrylic.
Why don't you do it, Daniel?
Because I'm holding it.
Damn, Daniel! Why did we even do this?
Well, we need something for our calculus project.
Yeah, but we could have come up with an actual plan before building something.
No, it's good because we can just like find the volume of the Earth or find the volume of something.
No, that's a bad idea. It doesn't even use calculus.
Terrible
Just look
idea.
up values for Earth's dimensions and then calculate volume with a very simple formula.
There's no point in just finding area of something geometric for a calculus project.
Maybe can I borrow your sword for a sec?
Sure, buddy.
This was a dumb idea.
Well, where are you going?
Daniel, no! Daniel! Daniel! No! Don't do it, don't do it!
That's not as cool as I thought it'd be.
Why did you do that, Daniel?
Come on.
I don't know, I wasn't thinking.
We worked on that for a solid 4 hours,
The
Dan.
entire project, Daniel. Wait. This reminds me of the intermediate value theorem.
Wait. How does that remind you of the intermediate value theorem?
Well, the sword stabs through two antipodal points, and because of the intermediate value theorem, shows that two antipodal points on the Earth will have the same temperature.
How?
Let's review the intermediate value theorem. The intermediate value theorem states that there is a number c in every continuous function between f of a and f of b. The continuous function, which is shown in the graph below, must cross the value c for it to reach from point A to point B, or from fa to f of b.
It is important to note that temperature is always constant. There is no point in time where temperature will jump from one temperature to another. It will always continuously go there.
That's all.
Let's call these 2 points on opposite sides of the Earth point A and point B. These 2 points are antipodal.
Now, we have mentioned the word antipodal before, so let's define it. Antipodal is an adjective, and it means relating to or situated on the opposite side of the Earth.
T of A is greater than T of B, and both numbers are greater than 0. Delta T of A, which would be equal to T of A minus T of B, is a number greater than 0. Delta T of B, which is equal to T of B minus T of A, is a number lower than 0. This graph shows change in temperature on the y-axis, and the x-axis represents the position along a cross-section of the Earth. Since T of A is above 0 and T of B is below 0, the intermediate value theorem states that there is a point C between A and B where delta T of C equals 0. This means that the two antipodal points T of C and T opposite C are equal at this point.
Here is the Earth, right? And here's point A and point B, the antipodal point. Now if we draw this cross section right here, this is what we're going to graph. So here's the cross section, bigger now. Here's an axis for temperature. Temperature of X. And then this is position. So from point A to point B, let's say the temperature steadily rises. Like that. I'm graphing around the line. And then from point B, continuing the circle back to point A, it has to end up at 0 again. It doesn't matter what the function is though. Do this, like that. We're good.
Now we're going to linearize this graph. This ellipses on the bottom will appear to be the bottom line in a linearized graph, A to B, and t of x would still be the y variable. And although this seems curved in this graph because it is the cross-section of the Earth, on a linearized graph it would be straight line. If we graph this, however, from B to A, as in this one, it can follow any pattern it chooses, but it will always have to pass across the same part as from A to B, and that is the temperature in which both of them are going to be the same.
This graph proves that there are two antipodal points with the same temperature on any cross-section of Earth.
What you say? That you only meant well, 'cause you did. What you say?